Hi, we are Group 19, and this is our Sentry Equipped Environment Monitoring System, S.E.E.M.S. My name is Danny Rodriguez, and I'm an electrical engineering major.
My name is Esperanto Elbon II, and I'm a computer engineering major.
My name is Noah Rooks, and I'm an electrical engineer.
My name is CDR. I'm a computer engineer.
Motivation behind S.E.E.M.S is that we want environmental security because it's a growing concern, especially in spaces where monitoring air quality, gas leaks, and other environmental factors is crucial. S.E.E.M.S addresses the growing need for proactive environmental security by adapting to dynamic challenges like gas leaks, air quality monitoring, and irregular noise detection. By integrating advanced sensors and real-time data monitoring, it provides actionable insights, instant alerts, and remote control capabilities for safer living and working environments. The background behind S.E.E.M.S, monitoring one's environment has become an increasingly important capability. Environment refers to interior areas like homes, schools, and labs. Monitoring methods range from simple to highly sophisticated solutions. So for our basic goals for S.E.E.M.S to function effectively, the Sentry and its partner application must work seamlessly together, with the Sentry using its camera and sensors to monitor the environment in real time. The application processes this data, providing users with sensor readings, alerts, and remote control capabilities. The partner application must be able to receive a steady stream of information from the Sentry. The partner application must process and display the stream of sensor information from the Sentry in a coordinate manner. For our advanced goals, the Sentry and its partner application collaborate to provide real-time monitoring, data transmission, and historical analysis by streaming live video and sensor data on temperature, air quality, and motion detection. The application processes this data, displaying live feeds, logging information for future analysis, and sending real-time notification about environmental changes or security. For our stretch goals, the Sentry streams live video and sensor data on temperature, air quality, and motion detection for real-time monitoring and analysis. Its partner application processes data, displaying live feeds, logging information for future review, and sending instant notification about environmental changes or security threats. Here's our table of engineering specifications. We wanted to specify the Sentry should draw a suitable amount of power from the battery which drives it, a power consumption of around 23 to 28 watts. The Sentry should move at a speed within a range suitable for interior environments. Our speed that we want is around 0.305 to 0.610 meters per second. The Sentry should take no longer than a suitable amount of time with respect to the MCU it runs on to switch states from off to activated. Our average boot up time is 30 to 60 seconds. Now for this part of the table of engineering specifications, we wanted to highlight the action and input delay. The method used to manually control the Sentry should be highly responsive and have low latency, around 10 to 100 milliseconds. While automation is crucial for S.E.E.M.S, manual control is necessary for immediate response to anomalies. High latency can slow reactions, reducing effectiveness in security situations. We also wanted to highlight in this table of engineering specifications the noise. The Sentry should be equipped with a microphone that can accurately and consistently measure a certain range of sound, around 35 to 120 decibels. Sound is often the first warning sign of unusual activity, making a high-quality microphone essential for S.E.E.M.S. Accurate sound detection allows S.E.E.M.S to identify threats like breaking glass or distress calls before they become visible. Lastly, on the table of engineering specifications, we wanted to highlight the connection latency. The Sentry should support both Wi-Fi and Bluetooth connectivity to enable and maintain stable connection with the partner application. Less than or equal to 250 milliseconds, we want to have the latency at. S.E.E.M.S requires a stable and responsive connection with the partner application to function effectively. Wi-Fi provides long-range connectivity for seamless data and video transmission, while Bluetooth ensures stable operation in areas with weak Wi-Fi signals or for close-range control. For our environmental sensor, we decided to go with the BME 688. This is an all-in-one sensor that can measure temperature, humidity, pressure, and air quality. It can detect a gas like carbon monoxide, ensures a safer environment by monitoring air quality. It's also cost-effective. It'll eliminate a lot of the other sensors that we could have gotten, but instead of getting a bunch of separate sensors, we decided to just go with one that could do all of them, all different things. And accurate and testable is temperature and humidity can be verified with simple methods. It supports further testing for enhanced environmental safety.
Our decision in choosing ultrasonic sensors was based on their balanced performance and cost efficiency, making them an ideal match for our project's needs, especially with ease of integration and detection range of up to about 4 meters, which is ideal for indoor presence detection. When choosing which ultrasonic sensor to use, we found 3 great options. Despite the advantages of these others, we still decided to move forward with the HC SR04. This is because we had prior experience with it from junior design and we already owned several of the units. The familiarity and availability reinforced our confidence in its performance for our indoor navigation needs. Electric microphones convert sound via diaphragm movement into an analog signal. They offer a balanced mix of sensitivity, affordability, and ease of integration, making them ideal for controlled indoor environments. We decided to use them as they meet our performance needs without the unnecessary complexity of MEMS microphones. Though, with a bit more time and experience to work with them, I believe MEMS microphones could make a great compact and durable choice. When selecting which microphone to use, we chose the CMA6542PF due to its simplicity, versatility, and plug-and-play design, which aligned well with our project's sound detection requirements. This module offers dual output, both analog and digital, along with adjustable sensitivity control by using its onboard potentiometer. This makes it very adaptable and cost-effective for basic sound detection and triggering, which fits our needs perfectly.
The choice of our camera model narrowed down to the ESP32 cam, RDW cam mini, and the Pixie 2 camera. Our reasoning for going with the ESP32 cam was the main interface that the ESP32 camera had, which included a Wi-Fi and Bluetooth integration within the ESP32 board. Given that we're also using the ESP32 as our main microcontroller of the board. In addition, our camera design is meant to be active only when the Sentry robot is active, or when the sensor alert is triggered, rather than a 24/7-hour surveillance. The ESP32 cam had a variety of choices within its lens design to choose from. The decision came down to the OV5640 cam model, since it provided much higher resolution and better image quality than the default cam module that came with the ESP32.
The right processing unit for the S.E.E.M.S needs to be able to handle connecting to all the sensors and peripherals previously discussed, have the resources to handle data collected from them, and be able to provide the means for reactions quick enough to guarantee both Sentry safety and quick user alerts to CenturyLink. The potential complexity of the path planning algorithms for the Sentry warranted consideration of single board computing, as certain algorithms require a lot more processing power than others. And so, the S.E.E.M.S processing unit initially consisted of one MCU and one SBC. The ESP32S3 was chosen as the system's primary MCU, and the Raspberry Pi 4 Model B was chosen as the system's primary SBC. Before finalizing the decision on processing unit composition, a decision on which movement algorithm to use was made. This will be discussed in further detail later in the presentation, but for right now, it should be known that a simple random walk was chosen. Almost any MCU can manage the overhead of this algorithm, and so the Raspberry Pi 4 was deemed unnecessary. On the ESP32, the most attractive features are integrated Wi-Fi and Bluetooth. These things are foundational to project success for connection to CenturyLink. The inclusion of a camera interface and native support for AI acceleration also make it a prudent choice considering system goals of working with the camera. We ended up choosing the N8R8 due to its high memory capacity and the high likelihood that our code will take up a lot of space. Mobility is probably the largest differentiating factor between S.E.E.M.S and similarly placed systems. This necessarily calls for choosing motors. The deciding factors between the three types considered here were cost, availability, and complexity. Though brushed motors are noisier, less efficient, and less precise than stepper motors and brushless motors, they are infinitely more available, a lot cheaper on average, and much simpler to use. The precision of steppers isn't required for movement, and brushless motors require extra hardware in the form of electronic speed controllers. Given the importance of mobility to the projects, ease of implementation is appetizing as well, as it will help us get the Sentry up and moving quicker. Before selecting any motor for the system, we need to make sure that we know the torque necessary to drive the Sentry for both its weight and its speed. We also need to make sure that the motors chosen can draw the proper amount of current with respect to our specifications. Not only will the motors act as a huge inductive load to the system, but they will also be the parts of the system that draw the most current and so be the most challenging to manage with respect to our requirement number one, that mandates lower power consumption. We plan on using two motors to drive the Sentry in a differential drive configuration. After some calculations, assuming 90mm diameter wheels and taking into account our speed requirement, we figured out that a single motor needed to provide at least 135 millimeters of torque and at least 71 revolutions per minute in order to achieve what we wanted. To balance power consumption with motor strength, we also want a supply voltage of less than 12 volts and a current consumption of less than 1 amp. After everything was decided, we decided to choose the Adafruit TT motors because they operated at 6 volts and had a working range of torque and speed well above what was needed. On top of that, because this project is not sponsored, their cheap cost was extremely attractive. Everything was perfect. Or so we thought. Hidden in the datasheet for the Adafruit motors was a small yet powerful statistic on the stall torque of the motor. Stall torque is the amount of torque that a motor provides when it is stalled or not moving. As a rule, the motor stall torque should be significantly greater than its operating torque. Adafruit listed this motor stall torque as 0.8 kilogram centimeters or 78 milliNewton meters. Not only is this 58% of our originally calculated result, but this value is also significantly less than the maximum torque listed, about 7.7 times as less. We tried to work with them, but after some calculations, it was evident that these motors wouldn't get us anywhere fast unless the Sentry was ridiculously light. Ignorance aside, new motors were needed. The process of calculating parameters remains largely the same. All that differs is that we lowered wheel diameter to 80 millimeters to make finding wheels easier. We used the mass of a similarly placed robot as an estimate, and we finally added 30% margins for safety and error. We also included the effective 3 wheels in the numbers because in a differential drive configuration, there are 2 drive wheels powered by motors and 1 caster wheel, all sharing the weight of the Sentry. At the end of it all, the Pololu 25D motor with a 75:1 gear ratio and encoders was chosen. This motor satisfies all of our requirements, including voltage, current, and speed. The manufacturer, Pololu, provides a much more comprehensive datasheet than Adafruit does for our previously chosen Dadova motor. Our torque requirement is roughly equivalent to 31 kilogram millimeters on this graph. Marked on this graph are the 2 points of interest for us at our desired torque: less than 1 amp of current consumption at approximately 750 milliamps and greater than 95 RPM at approximately 117 RPM. These motors are actually perfect for S.E.E.M.S. The only issue is that the potential to draw greater than 1 amp of current. This can be managed in software and will be explained later. Further examining the behavior of brushed DC motors, the need for a motor driver becomes apparent. Without one, a brushed DC motor spins at a speed proportional to its supply voltage, and it spins in only one direction unless the terminals are manually switched. A motor driver allows for both speed and direction to be more precisely controlled, and this is important for sensor movement capabilities. It should be able to move left and right, and to move forwards and backwards, so as to allow it to cover the environment properly. Looking at the motor drivers available, the only valid choice were H-bridges. They use transistors and so respond quickly over their mechanical relay counterparts. They provide speed control via PWM and bidirectional control through their structure. Further, H-bridges are really the only proper choice to do anything robotics related. The most important parameters for motor driver selection are driver operating voltage and driver continuous output current. The operating voltage should be able to accommodate the supply needed to power the motors, and the driver should be able to handle the motor stall current. Motor stall current is the current a motor draws when it is stalled. It is important that a driver be able to handle this at 2 points in a motor's normal operation. At the beginning, when a motor starts up, because it will momentarily draw its rated stall current as it starts to overcome its initial resting state, and at any point when a motor stalls and it becomes unable to move. The Toshiba TB9051 FTG is an automotive motor driver with exactly those specifications. The cost makes it attractive as well. As an added benefit, there are several protection features integrated into the IC. The most important one, it seems, is the overcurrent monitoring feature, which will be discussed later.
Being a mobile security robot, the battery is one of the most important decisions. Initially, we considered using a nickel metal hydroxide battery because they are safe, simple to integrate, and comply with our lab guidelines. However, after further evaluation, we chose lithium-ion batteries instead. These are significantly smaller and more power dense, which is essential for our compact design. They also offer much more compatibility with wireless charging, which is a key stretch goal for our project. Although the nickel metal hydroxide batteries provide a reliable plug-and-play option, the superior energy density, compact form factor, and wireless charging support of lithium-ion batteries make them the optimal choice for our robot's power system. The change in motors made us need to increase up to a 12-volt battery, changing our selection to the Talent Cell 12-volt lithium-ion battery, which offers 11,000 mAh. This battery supplies a stable 12-volt output that directly powers our motors, while also providing ample capacity to ensure that we get at least 2.5 hours of operation. To give stable voltage levels, we've first chosen the MP2338GTL, a switching regulator that with over 90% efficiency steps down 12 volts to 5 volts. Next we use the S.E.E.M.S 1117, a linear regulator, to provide a stable 3.3 voltage supply. It offers low noise output, which is perfect for more sensitive components like our ESP32 room. By combining these two regulators, we hope to ensure that every part of our system receives the appropriate voltage while balancing efficiency and noise performance.
This diagram represents the core architecture of the S.E.E.M.S, highlighting the components and their connections and their assigned team members. Each block is assigned to a specific team member for development and implementation.
Anyone control movement in our mobile app will be provided for the user to override and take control of the robot random walk movement. The user interface for movement should be simple for user to interact with and grasp the controls. An important aspect of the control is the user inputs should correspond to the sentry robot while it's roaming around. The choices we consider for the user manual movement were a virtual game console controller design, a gesture-based controller, and a press and command controller. Each controller design had a lot of similarities between them, and a very friendly UI that scales down the learning curve. We decided to pursue a virtual game console control design, mainly due to the familiarity of the style, as it is the most popular and common type of controller. Its design will include a directional pad that will allow movement in all four directions and a joystick for horizontal panning.
Having the sentry be autonomous is a large part of this project. Thus, we need to look into path planning and movement algorithms. As our system is a monitoring system geared towards movement in the environment, coverage is a significant parameter. The best algorithms to use fall under a class known as simultaneous localization and mapping, or SLAM methods. These algorithms form a map of the environment through sensor fusion and allow the robot to move through it almost seamlessly. They are typically very effective, but also very expensive, both computationally and financially, requiring quality LiDAR and quality cameras. Random walk is simple. Take the robot, send it forth in the environment, and allow it to make movements dictated at random. Perhaps counterintuitively, it is very effective at covering a majority of whatever environment it is implemented in. The random walk algorithm was chosen because of its high success at coverage and interior environments, low computational overhead and complexity, and low cost. The only downsides are obstacles, but this can be accounted for with sensors.
Choosing a programming language and an environment to build came primarily down to knowledge and comfortability in the workspace of the language environment. The selections narrowed down to React Native, Flutter, Swift, and Kotlin. Although Flutter is on the rise and seen as an attractive option to learn, we chose React Native with JavaScript and TypeScript as our main programming framework for our mobile application. Swift and Kotlin can be developed in their respective platform and exclude us from implementing the app in a cross-platform format. To produce a continuous stream of video over the internet, we needed to figure out what format are the video being transmitted in, and how do we obtain the video to display to our mobile application. Our options were the motion JPEG or real-time streaming protocol. The motion JPEG protocol streams every frame as a single image one after the another, in a seamless pace that appears as a continuous video. Our pick for the motion JPEG was complementary with our design, as we did not need to deliver audio transmission. In addition, the real-time streaming protocol will provide us with additional unwanted latency to the user screen. Moreover, the ESP32 CAM has built-in support for this format and allows of ease of integration of the protocol.
In code, the motor drivers will control the motors by taking in different combinations of PWM inputs. Alternating inputs allow motors to be off, turning clockwise, or turning counterclockwise. Pairing two motors in differential drive and driving them correctly gives movements in the cardinal directions. These PWM signals are provided by dedicated channels from Espresso's motor control PWM API. With the motor driver's current monitoring pin, we will dedicate a pin on the MCU to reading its voltage level. That level corresponds linearly to the amount of current that the motor is drawing. If the motor is deemed to draw over between 1 to 1.5 amps, the software will be set to stop the motors by disabling the drivers, thus preventing stall from being reached and lowering overall average power consumption. Output from the diagnostic pin immediately stops the drivers until software deems it safe to restart operation. The sensor will collect data and information from each of the sensors and use that data to inform its decisions. The overall system will be task-based, but with the occasion interrupts for select sensor readings or timed events. Tasks will be created to collect data by polling each sensor at a constant predefined frequency and to communicate with CenturyLink through Firebase. The diagram shows an example data flow through the system from sensor to CenturyLink. As described earlier, the simple random walk method does surprisingly well at covering a space. It does very poorly, however, at avoiding obstacles. To combat this, the random walk implemented in the Century will use the included presence sensors for obstacle detection on top of the human presence detection. In this way, a virtual barrier is placed around the Century, not letting it hit anything immediately around it. To get the best randomness possible, we'll use the ESP32S3's true random number generator. It is based on hardware and randomizes numbers with respect to noise from the integrated Wi-Fi and Bluetooth antenna. To achieve the goal of notifying users of changes within their chosen environment, the Sentry will have an internal alert system run on customizable measurement thresholds. This system will interact directly with the Sentry sensors and with Firebase, updating the database whenever any anomaly is detected. An anomaly is a major change to one of the measures of environmental quality listed in the table shown here, and it is found by looking through recent measurement history within the code after each sensor reading. The second diagram is a flowchart describing how an anomaly might be detected. Here's an overall class diagram that represents the Sentry sensor and drive system. This describes modules created to wrap the functionality of each sensor and motor in order to make the system easier to work with by means of abstraction.
Firebase is our cloud service that will provide us the needs of storing and managing data from our robot to provide the information in the app. The most subtle feature of Firebase is the real-time integration that can instantly update the sensory data and allows synchronization with the app readings. Furthermore, the Firebase Cloud Service provides us with an authentication that can handle user information with high level of security and encryption to prevent the user data being leaked. The communication between the Sentry and the mobile app will require a means to establish a connection between them. The Wi-Fi module will connect our microcontroller to Firebase to send the sensors information and retrieve them. On the other hand, the Bluetooth module will be similar to a one-time use setup to send the information of the Wi-Fi credential to the Sentry robot to connect the module to the internet. Software outline to visualize how the app will interact. Our main refer to any data that will be needed to manipulate or change needs to communicate with our database, which houses all our user information and our mobile commands to the Sentry. The only exception that doesn't rely on our database will be the streaming platform for our video feed. An overview of the potential layout of our app here demonstrates our 4 main pages that we have in our app: the sign-in page, the main dashboard page, a customization tab, and the camera feed with the manual controls. The sign-in page will authenticate and certify the user's credential. With the dashboard page, it will show the user the sensor data report from the environmental sensor. Our customization tab will ensure that the user can change the level of however he or she wants the sensory data to be. The last tab will provide the user with a camera live stream when requested, and the ability to move the robot around with the corresponding commands.
Our main PCB is a 2-layer board measuring 206 by 106 millimeters. Down the bottom you can see our voltage regulators as well as the new barrel jack plug-in with a standard 2-prong connection above it in the event that our new battery needs to be replaced. At the top right is our ESP32 room, followed next by the USB-A connector and the USB to UART bridge controller. On the left and right you can see the connections for our motors and motor drivers with direct 12-volt connections running to them for the motors. On all 4 sides are the ultrasonic sensor connections. They, like most of our sensors, will be spread to the edges of the Sentry unit, so the placement doesn't need to be exact on the PCB. Next, you can see the connections for the microphone, the BME 688, and lastly, the ESP32 cam.
This is our overall hardware schematic. It shows the complete electronic design of SEEMS, showcasing how different hardware components interact to enable surveillance, environmental monitoring, and real-time communication. On the right side, there's a schematic diagram showing how each ultrasonic sensor module is connected. Each sensor module has 4 connections: power plus 5-volt trigger, labeled as trig, echo, labeled as echo, and ground. The 1K ohm resistor is used for the echo pin connection, while the 2K ohm resistor is used for the ground connection.
For our breakout boards, we were able to replicate the designs of the already obtained modules. We made the decision to slightly enlarge the PCB footprints and component placements on the microphone and BME 688 boards for easier assembly and troubleshooting. The motor drivers, however, were limited on how much they could be scaled since they plug directly onto the main PCB.
This schematic diagram shows the microphone. This schematic diagram detailing various components and connections, including resistors, a voltage regulator, LEDs, and an integrated circuit connectors, and the CMA 6542PF MK2 component. Electrical connections represented by green lines, including key connections such as the power supply, series and parallel resistors, indication LEDs, a voltage regulator, and integrated circuit and connectors for external signals. This diagram provides an overview of how the CMA 6542PF component and other components are integrated into the SEEMS PCB. It highlights their crucial roles in ensuring the proper functioning of the PCB. This schematic diagram shows our environmental sensor, the BME 688, its connectors pins within the SEEMS PCB. The diagram is divided into several sections, each enclosed in a dashed red box labeled with different functional blocks. These blocks include the power supply with a voltage regulator, capacitors, and power flags, an on LED with the resistor and green LED, I2C pull-ups and shift with MOSFETs, and pull-up resistors for level shifting, and connector JP1 with pins labeled for various connections. The BME 688 sensor section includes pins for power and I2C lines, while additional components like a resistor and a diode support overall functionality. Here we have our motor drivers. This is an electronic circuit schematic diagram that has a voltage regulator circuit at the top left, a microcontroller in the center, and various connectors and passive components, resistors and capacitors throughout the diagram. The voltage regulator circuit consists of components like a diode, a transistor to regulate the input voltage Vin to a stable output voltage Vout. The microcontroller is connected to various pins and components, including resistors and capacitors and connectors, which facilitate the control and operation of the circuit.
We use a 12-volt battery as a central power source, which not only drives our motors directly, but also feeds voltage regulators to supply our sensitive electronics. These electronics will draw roughly 600 milliamps at 5 volts. Each motor has a stall current at 5 amps. However, under normal conditions, we expect to draw around 1 amp, so the motors average about 2 amps in operation.
The first Century prototype was more of a proof of concept. It was built from cardboard and duct tape and ran a significantly reduced version of what SEEMS promises. A short clap or other loud noise would be detected by the microphone, simulating an anomaly. This would prompt the Century to begin moving forward. The Century would then move until the front ultrasonic sensor gave a reading that broke the default barrier around the Century, indicating that it should stop immediately. The second prototype will be built soon. It is to be made of 1/8 inch MDF laser cut to specification by the TI lab and then put together. Each system component has its dedicated place, with the battery going to the bottom level alongside the ultrasonic sensors. This is to ensure that the Century's center of gravity is low and that it can detect obstacles as low to the ground as possible, respectively. The PCB has a dedicated spot on the second level, and the third level is split amongst the camera and mic, with the BME having sole access to the topmost level. This prototype will be stronger than the first and is more representative of our vision for the Century as well. After the construction of the second prototype, the immediate plans include beginning design of the panels or some other form of enclosure to protect the interior of the chassis. We also plan on choosing a mesh-like material or fabric to cover the top layer of the chassis where the BME is located. In order to function properly, it needs consistent airflow. We will also more thoroughly define how the battery will be charged within the prototype. That might be with some separate charging station logic and dedicated contacts built into the Century for contact charging, or we might end up just using a plug-in wall charger. Finally, we'll pinpoint the actual position of the camera and ultrasonic sensors on the prototype for optimal monitoring and measuring.
Our hardware testing plan focuses on several key areas. First, we will perform PCB and breakout board testing to verify that each board functions correctly, systematically going through and testing all the power lines have the correct values. Next, we'll conduct stress and performance testing, evaluating motor performance, sensor accuracy, and overall system reliability while under load. Finally, we will ensure proper integration and communication between the main PCB, the breakout boards, and communication modules. When testing our microphone module, we will connect it to the regulated 5-volt rail on our main PCB to then capture its analog output. Our goal is to verify that the analog output remains stable and within the expected voltage range under different sound conditions. We also adjust the on-board potentiometer to fine-tune the sensitivity and ensure that the sensor's response is consistent across various ambient noise levels.
During our initial testing of the camera's performance, we observed that the device became unresponsive and non-functional after running the video protocol for a few minutes. While considering alternatives, including replacing the ESP32 cam with a different module, we investigated the issue further and identified the cause. To address the overheating, we installed a heatsink on the lens, and after additional testing, we confirmed that the camera model now functions as intended.
After programming the enhanced random walk, its average room coverage will be tested by placing the sentry in rooms of varying obstacle density and successfully measured by observing how little of the room was left unobserved by the camera as it moved around. Obstacle detection will be tested in a similar manner, and success will be measured by observing how infrequently the sentry bumps into obstacles. Later testing in various different types of rooms and environments will be done as well. Tests will also be conducted to verify the accuracy of the sentry's anomaly detection and notification system. Different kinds of stimuli will be given over varying periods of time, and the sentry's reaction to each stimuli will be observed. Success will be measured by the frequency of real anomalies the sentry detects and notifies about. Stimuli will, of course, be loud noises to simulate furniture falling, or temperature variations to simulate fires, and finally, humidity variations to simulate burst pipe conditions. In testing the ultrasonic sensors for presence sensing and obstacle detection, it became important to realize that the standard method of pulsing the sensor for measurements to be taken did not mesh well with the task-based system being created. The task-based system allows other tasks to be created and performed while another task is delayed with behavior known as non-blocking behavior. The old way of pulsing the sensors was blocking behavior, and while this might not be an issue for one sensor, for 4 sensors being pulsed in a row, it might present some sort of a problem. So to that end, the method of reading ultrasonic sensors was updated to use interrupts and non-blocking delays instead.
This table shows the gross total cost for each of the major components of our project, which includes the associated shipping fees and tariffs. The biggest costs here are the PCBs with the required components and the motors. With all these components here, the total comes to be about $650.
For our team distribution, Sprandio is our group leader and in charge of our embedded programming for the MCU and our motor drivers, as well as designing the enclosure design of our robot. Danny is focusing on validating the system and circuit components and supporting the PCB assembly. I'm in charge of the mobile app as well as aiding the sensory system and the mechanical housing design. Noah is responsible for PCB design and assembly within the addition of designing the power management system.
This slide marks our current progress. The main PCB design we have completed. It took us about 10 weeks. The daughter board's PCB design, it took us about 5 weeks and we completed it. Ordered PCB and parts took us about a week and completed it. We're still working on the partner app and embedded software that's currently in progress and is still under development and integration.
Here is a Gantt chart dictating the timeline of future progress for S.E.E.M.S. The next immediate goal to prepare for is the midterm demo, and before we get to that, we need to construct the next prototype, ensure a camera stream that flows consistently to CenturyLink, ensure that alerts and environmental readings flow to CenturyLink from the Sentry, and finally build and test our movement schemes as described. Post the midterm demo, if necessary, a final prototype will be constructed with lessons learned from the second, and by that point, hopefully only software kinks with respect to authentication and other smaller things will need to be worked on in the weeks before the final live demo. And with that, our presentation is complete. Thank you so much for watching, and please let us know if you have any questions.